wasn't crazy. It did come up on the big screen for a moment, didn't it?
Yeah. There you go. Yay.
The amount of power cycling that needs to happen before any of the AV in this building works is not very impressive.
PowerPoint myself.
Yeah. One.
Is that going to work?
Yeah, I'll make it work.
Okay.
Thank you.
Yeah. So is this just permanently fixed over a whiteboard? Did they just drill some holes right through? You know, when we get a semi-permanently brainstorm, you know, where else are we going to pin our ideas?
That was pretty good.
Well, exactly, right? Like, it's not even... It's going to have, like, extreme permanence.
Okay, so I guess the goal today is to try and make sure that everyone can start writing some short tactics.
Recording for James.
I'm recording for James, yep. No one said they wanted to Skype in, so video afterwards.
James said something to that effect on the day.
That he would?
That he might try.
Yeah, okay, I think I'm pretty sure I don't have Skype open. I sent a message on Zulip saying where I was on Google Hangouts and who I was on Skype. So
Yeah,
we'll see if
sure.
yeah. Okay. Yeah, but I wanted to spend a little while at the beginning talking about monads, because they're something we definitely need to meet when we start writing tactics. Okay, so who has I know some of you have done some programming in Haskell and some of you haven't. So who's seen Haskells already who's seen monads in Haskell or some other programming language? Excellent. Easy. Everyone's in exactly the same boat. Okay. So let me write a little program, and then we'll stop and understand what on earth is going on. So that's not a lean file yet. Okay, so there we go. I defined a list, and let's define some function that takes a natural number and spits out, say, the list of that natural number and 7 times that natural number. Oops, colon equals. Can everyone see up there? It's okay. Yep. Okay, so let's now write a little function that does something a little strange. what I'm going to do is I'm going to say do x in x, y in gx, return y. And that compiles, although it's a syntax that maybe no one has actually seen or used before. What's it going to return? If I type eval z here, what happens?
Like a list of 3 lists with like 1, 7, 2, 14, 3, 21.
Almost, but not quite. So let's see what it returns. How do I see the return? Yeah, it's not a list of 3 lists. It's just a single flattened list with the 6 entries, 1, 7, 2, 14, 3, 21. Okay? So, so we need to understand why this piece of syntax is producing that output. If you've used Python, many people probably have at some point, there are 4 comprehensions, which is this funny syntax for building lists of things, and they sort of achieve a somewhat similar goal as this. Okay, let's write another. Okay, so notice in fact that this z here was a list of natural numbers. Okay, we didn't say it explicitly, but Lean worked that out for us. Okay, let's have another function, say that says I don't know, if 2 divides n, then sum n over 2. So sum is a constructor for the type option, and else none. Okay. And now let's define a function y, say natural number, to be, let's do n in hn, n in hn, n in hn, return n. Okay. If I now type eval y of, say, I don't know, 24, what's going to happen?
Return 3.
Not exactly, yeah, almost.
List.
It's going to return sum 3.
Okay.
Yeah. And if we eval y of 12, it'll return none. Okay. So in each case, what you should think of as happening is in this line, say, you should read this as sort of, pull each x out of big X, and then pull each value y out of g of x, and then return that y. Okay, so this had the effect of sort of iterating over x, and inside each of those iterations, iterating over the value of g of x. Okay. And in some sense, this was doing the same sort of thing here. It was saying, well, whatever h of n is, it's either something or none, and so try and pull out a value. Then try and apply h to that again and pull out the value. Apply h to that again and pull out the value, and finally return what you got. When we ran eval y of 12, at this step here, h of n had become, that was h of 3 at this point, so there was no value to pull out of it, and so the whole sort of do loop just sort of short-circuited at that point and didn't continue down the chain. It just returned to none or at that point already. Okay, so how is this working? Well, in both cases, when Lean sees the do loop, it is inferring that it needs a monad instance. So let's check that we can get monad instances. So example, monad list by apply instance. Indeed, that finds one. And let's just give it a name so we can look at it and find out where it actually got it from. So now, hash print monad list. And it has the unsurprising name list.monad. And so we can print list.monad, which is the actual built-in one. And we could jump to the definition of that list.monad. Okay, so it's over here, and it's probably way back down in the guts of Lean. Yeah, it's in Lean itself, not in MATLib. It's there really early on. Okay, so they defined this thing called monad, and it was some structure with three fields, pure and map and bind. So we're going to have to go and work out what those things are in a moment. There's also actually a second instance here, is a lawful monad, which has a bunch of axioms about the behavior of that monad. Because monads were stolen and appropriated by computer scientists, they have funny habits like thinking of the monad and the rules about the monad behaving properly separately. Like computer scientists might talk about a ring and a lawful ring, where like the multiplication is actually associative. So that's all that's going on here. They've just split out the axioms as a separate instance. Okay, so let's now, given that we had this other example that worked with option, we know that we can probably look up by apply instance a monad option. But let's just build one ourselves and see what we need to do. So def option monad of type monad option colon equals begin end. Okay, so we need a monad option. We saw just by looking up there a moment ago that it was a structure. So let's fill in an empty structure. Ooh, something very sneaky goes on here. Can anyone tell me what happened here?
Lean do everything for you.
Lean did everything for us because it saw that monad was a class, and so it actually went away and just grabbed the default instance of monad option that it had already and used that to fill in all the fields in the one we're writing here. So that was a bit unhelpful. So let's write pure equals sorry, bind equals sorry, and what was the other one? Map equals sorry. Okay, and those were the three things that we were meant to specify in order to construct a monad. So let's just look now by replacing the sorries with begin ends and see what it is that we're meant to produce. Okay, so what does pure do? Pure says, for every type, you need to give me a function from that type alpha to option alpha. Okay, does everyone know a function that we could use here? We'll worry later about the rules these are meant to satisfy. Let's just try and construct the damn things. What could go there?
So is option this sum thing?
Yeah, option is the thing that is either sum or none. So let's
We just want it to be some it, right?
yeah, exactly. Yeah, so option here is just this inductive type with one constructor none and another constructor sum. That's exactly this. It's a function from alpha to option. Yeah, so I think we can actually write here option.sum, or maybe we need to put an ampersand to give it because we wanted that argument to be explicit. Okay. What's bind meant to be? Well, bind is meant to be. Actually, so let me leave out bind. Yeah, okay. I'm actually going to leave out bind. Can I leave out bind? Is that bad? No, because then it's pulling in an instance to do that, isn't it? Yeah, okay. We need to give it bind. Okay. Okay. So what does bind do? It's a function that depends on two types, alpha and beta. And then it says, given an option alpha and a function from alphas to option betas, it gives me an option beta. So how could one do that? There's kind of only one possible definition of this function, regardless of what the laws are of a monad. There's only one way to write such a function. Well, that's not true. That's true. There are two ways to write this function. What are the two ways to write this function?
You could send everything to none. Or you could
Exactly.
do it properly.
Or you can do it properly. Yeah. So the way to do it properly, so we will write this as a little lambda. So we had a lambda types alpha and beta, and an option and a function. Let's just make sure we got that right. Yep, so alpha and beta types. O is an option of alphas, and F is a function from alpha to option B. And the only sensible thing to do is if O is none, return none, and if O is something, apply F to it and return whatever you get. So let's in fact just write that. So we can write match O with, and we can write it all in one line since we're doing that at the moment. Okay, and lean compiled, so that must have been the right definition.
I reckon you don't even need parentheses inside the match.
Oh, we're around the sum?
Yeah.
Oh, Keely saved us 2 characters. Excellent.
Really golf.
Okay. And what is map meant to be doing? So how do you define that? We've got a function from alpha to beta, and now given an option alpha, we have to produce an option beta.
Option F of alpha. Wait, no, that's not going to work. Sorry.
It's going to be pretty much the same thing.
It's non-useful, otherwise you evaluate it. Some of that.
You evaluate if it's sum. The point is you can pull out what you had inside the sum and apply the function to that and wrap that inside sum again. Yeah, so let's do that. So this time the order of arguments is a little bit different. We have 2 types, alpha, beta, and our function, and then finally we have our option. And again, we were meant to match O. And if it was none, we did none. And if it was sum A, we returned sum f of A. So it's slightly different. There has to be that sum wrapped around the f of A there, because we had to return an option in this case. No, sorry. Lean is upset. Why is Lean I didn't put a comma after the O. Great. So we defined then a monad on option. Let's have a look also what rules we're meant to have satisfied here. Oh, and again, it's pulling in. Oh no, there we go. Pure bind and binder sock are the 2 things that apparently it wants us to prove. So we've got pure bind and we've got binder sock. And let's see what it is we're meant to be proving in each case. For pure bind, well, let's run intros so it's a bit easier to read what's going on. We're meant to be proving that option.bind of sum x applied to the function f is f of x. Okay, that is maybe a reasonable rule. We can probably at this point just say that's reflexively true. Yay, okay. And binder sock, let's run intros. So here, what did we get after we ran intros? We had an option of alphas, and then we had a function from alphas to option betas, and a function from betas to option gammas. And it said we could do 2 different things. We could either, do this or do that. I'm not quite sure. Yeah, so how to say it. We could take the function that binds f to x and bind that to g. Or we could... Sorry, we could take the result of option bind xf and bind that with g. Or we could just take... Yikes. Yeah, so confusing. How are we going to prove this one? Even if we don't know what we're proving, we should know how to prove it by this point.
Cases.
Yeah, so exactly. As soon as you run cases on X, then because bind was just defined by pattern matching, everything will just desimp away hopefully, and we can. Oh, desimp didn't work.
Twice and it kills them both.
Oh, we don't even. Okay,
Yeah.
We didn't need to desimp. Okay, we just needed to ruffle. But you could only do that after the cases. You couldn't have ruffled before the cases. Okay. Okay, fine. So we've sort of learned how to build monads, but maybe not. We maybe don't yet understand what bind to sock was actually saying. Okay. Let me just actually, before we go on, give you some examples of how we can do slightly fancier things. Actually, no, that's not the one I want. I want this one. Yeah, so let's define a slightly different version of Z. Z prime. So this, remember, was the one that returned that 1724321. We can also just put in additional sort of flow control structures here. We could just say something like, guard, it is not the case that 3 divides y. Okay? And if we do that, then we only get a smaller bit of the list. Okay? We only got the stuff where 3 did not divide y, or we could do, I don't know, y is less than 10. I guess guard wants parentheses around its argument. And then that only returned 1723, but whatever the other numbers were, 14 and 21, got stripped out. Okay, so you can see that with there'll be more things that we can do alongside guard and this little arrow, but somehow the idea is that we can do almost imperative style programming inside a do block, and somehow that's being made possible under the hood by the existence of these monad instances. Okay, so fine. At this point, we could, I guess, go in 3 different directions for a moment. We could talk a bit about the abstract nonsense of what monads really are. We could talk a bit about what computer scientists think monads are, or we could just press on with the most interesting example for monads for today, which is the tactic monad. What do people feel like? We'll get to all of it. We'll certainly get to the third one. The question is how much we detour through the first 2.
Last one.
Abstract nonsense? Okay. We shouldn't do too much abstract nonsense. Okay. So, have you guys heard of justification? Justification is one of my favorite mathematical techniques. So there's categorification, where like you take some mathematical object and you replace everything inside with something 1 category level up. Like you take your numbers and you replace them with the dimensions of vector spaces, and now there's a whole extra category level because you've got like linear maps between the vector spaces instead of just the numbers sitting there. Or there's groupoidification, where like you realize that maths is more interesting if you allow your algebraic objects to have multiple sub-bits. Anyway, let's not worry about what groupoidification. Justification is just a joke. It's a play on these things, which is just whenever a mathematician says, oh, an x is just a y, and say something much more complicated and difficult for y than the original x. That's justification. And so I'm going to just do justification on monads now. Okay, so a monad is a monoid object in the category of in the monoidal category.
This is getting pretty hardcore.
Of natural endomorphisms of a functor. Whoa. Okay. Oh yeah. Sorry. It's just. I'm on it. Okay. So what on earth is going on there? So the very first thing that you've got, okay, and and to a computer scientist, let's say to a computer scientist, all functors are functors from type to type. Okay, they don't know about other categories. They only know about the category of types, and so that's how you specialize the real definition to the computer science definition.
Do people know what categories are?
No, but that's okay.
Right.
Okay. So let's start explaining some of the words in here. So first of all, there's a functor, but to even say first of all there's a functor, that means that first of all there are a pair of categories, and it's a functor from one category to another category. So who knows what a category is? Just by a show of hands or wobble of hands. So lots of wobbling hands. Okay. So So a category just consists of some collection of objects and some collection of arrows going between those objects. You can think of those arrows as they could be that the objects are actually sets, maybe equipped with extra structure, and the arrows are just functions between those sets respecting the structure. So a classic example might be the category of all rings. The objects are rings, the arrows are the ring homomorphisms between pairs of rings. And then type, the computer scientist's only category, the objects are types in your programming language, and your arrows are just functions from one type to another. Okay? And so it's important in a category that you can compose arrows. If I've got arrows from A to B and from B to C, I can compose those and get a new arrow from A to C. I've got an identity arrow from any object A. I've got an arrow from that to itself. And those arrows behave in sensible ways. Composition is associative, and the identity arrow acts like an identity. Okay. A functor then is just something that takes one category and turns it into another and like sends it to another category. So every object turns into an object to the target category. Every arrow gets sent to an arrow in the target category, and all of the structure is preserved. So compositions of arrows are taken to compositions, identities are taken to identities. Okay, so what's an example of a functor?
Pi 1.
Pi 1, great. What's that a functor to and from? From and to.
Topological spaces to groups.
No, almost, but not quite.
Is it pointed topological space?
Yeah, pointed topological spaces to groups will work, because pi 1 depends on a base point. You only get a group out of it. So the slight, what could you say if you really wanted to start from topological spaces? Or what could you say pi 1 is?
If you read the NLab,
Yeah,
you would have accidentally seen it.
So pi 1 you could also think of as a functor from topological spaces to groupoids. So groupoids are just like groups, but they've been groupoided. They've been groupoidified. Okay. So a groupoid.
So pi 1 takes a topological space to its fundamental group.
Yeah. Oh yeah. Sorry. Yeah. Excellent reminder there. Yeah. So who needs a reminder of what that pi 1 is? Yeah. Okay. So you're gonna know. Okay. So pi 1.
Algebraic topology is a prerequisite for this course.
Yeah. All of maths is a prerequisite for all the rest of maths. Okay. So you've got some topological space. Think maybe like my coffee cup, the surface of my coffee cup, teacup. So pi 1, you have to specify a base point, and then pi 1 just consists of the set of all loops on the space that start and end at the base point, but up to an equivalence relation, which is known as homotopy, which basically means you can deform the path around. So you've got a one-parameter family of paths that never changes the endpoints. And how could we make that a group? Yeah, you could follow one loop around, and then you could follow another loop around, and forgetting somehow that composed loop happened to pass the midpoint, pass the base point at the middle. Yeah, that's just a loop, and it's pretty clear that. Oh, and the inverse, we really get a group, is if you follow some loop around, and then follow that loop backwards. You can always retract that back to the constant loop at the base point. Okay, so it's homotopic to the trivial loop, the identity. Okay. So, fine, that's a group, but it depended on the base point. Okay, fine. So let's not worry about groupoids and all that garbage. Okay. So that, but we need to know it was functorial. We just said it was a functor. So this was some gadget that took topological spaces with a chosen base point and sent them to groups. If it's meant to be functorial, we need to say that every time you have a map between topological spaces, a continuous map between topological spaces, because those are the arrows in the category of topological spaces, we need to produce an arrow in the category of groups, i.e. a group homomorphism. So how do we, if I've got a loop, if I've got a loop in one space and I've got a continuous map to another space, I need to produce a loop in that new space.
And it maps base point to base point.
It's a map in the category of pointed topological spaces. So it's a continuous map that takes base point to base point. Good. Yep. So how do I deal with loops?
Send them via the continuous map.
Yeah, I mean a loop just means a map from, I don't know, S1 or the interval or something into our space. And so you can just compose that map with the map forward into the next space. And now it's a loop in the target space. And it's pretty easy to check that respects composition. If you compose two loops here and then map them across, it's the same as mapping across and then composing. Okay, so continuous functions got turned into group homomorphisms. Okay, so that's a functor. A computer scientist would never list that as their first functor. What? G'day, Aaron.
Hey, sorry.
It's okay.
I forgot this was on.
So, very, very briefly, we did a little bit of a demo at the beginning of writing these do blocks, which you might just catch up on later. This file, will be in the repository, or I can even just stick it on Zulip right now if you want to read along and catch up.
And you've been recording what you
And
said.
there's also video of all of this so far. Yeah, I'll just stick it on Zulip quickly for you, and then you can just quickly read through that while we continue talking. Okay, and then we've been talking for a moment. I've been trying to say the abstract nonsense of what a monad is. But there's a bit to do because I have to explain what categories are and functors are and all these things. So we're not going to get there. Yeah. Okay. So but what we can do is have a think about a computer scientist's example of a functor. So the only category they know about is types, and so the only functors they know about are functors from type to type. So what's an example of a functor? From type to type.
Alpha to list alpha.
Yeah, the clue is that we've just seen two of them. That list and option were both functors. So given a type alpha, we get a new type list alpha, and this field map of a monad was expressing the functoriality of that association. That if we well, maybe it's not so obvious in the yeah. So if we go back here and just look what sort of thing we were meant to be producing in this map statement. Let me not introduce the O. We had this function. So here, given an arrow from alpha to beta, we were meant to be producing an arrow from option alpha to option beta. Okay, and that was exactly the functor acting on morphisms at that point there. Okay, so it's a little bit to a mathematician's eye, it's pretty darn strange that when you define a monad, sort of the pure and the bind and the map are kind of somehow all at the same level. To a mathematician's eye, sort of bind is much more fundamental. That's the first thing you say about option. It doesn't just take types to types. It takes functions between types to functions between the new types that get produced. And then pure and bind are part of all of this complicated stuff about monoid objects of natural endomorphisms and yada, 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 yada. Okay, so okay, let's do a little bit more. Let's do a little bit more abstract nonsense. Okay, so let's keep going here. So we just said a functor from C to D. So those were both implicitly categories. Takes objects C to objects D, and arrows in C to arrows in D. Respecting all the structure. Sources, targets, identities, composition. So arrows have sources and targets. So respecting sources and targets means that like each arrow gets sent to an arrow whose source is the image of the source and whose target is the image of the target, and so on. Okay. So the next notion that everyone should learn is a natural transformation. So here we're going to have a functor f. Now, I'm going to use that notation. That was the /func arrow, which is not at all universal notation for functors, except that it's what gets used in Lean. So you might as well use it. So a natural transformation goes from a functor from C to D to another functor between the same categories. Okay? So what does it do? So what you should think is it compares the values of f and g. That is, for each object x in the source category, it gives an arrow in the target category from fx to gx. Okay? So we had two different ways we could have sent x over to d, and a natural transformation is just a comparison between them in the sense of an arrow. And if you really want to learn the lean syntax while we're at it, we'd actually write f.objects to say it's the sort of part of f that is modifying objects rather than modifying morphisms. Okay, and it satisfies a compatibility condition. So for every arrow in C, maybe some f from x to x prime, and here I did something a little strange. That arrow there is not the normal arrow that you've been writing for functions in lean. That was actually a /hom arrow, which, again, in normal maths, no distinction is made between these two arrows. People just write an arrow for morphisms in whatever category. But the magic of the category theory library in lean says that when you write that /hom arrow, it automatically interprets this as whatever the appropriate notion of morphism is between these objects, not necessarily just a functor. Just a function. It might automatically be a continuous function, automatically be a ring homomorphism, or whatever it needs to be. Okay, so for every arrow, what can we do? Well, we can either get from so we've got two arrows now. We can either start at fx, so f of x, and then we can go to f of y, okay? And then we can go to g of y, or we could start at f of x and go to g of x and go to g of y.
Is y x prime?
Thank you. Yep, let's change x prime to y. Yep. So can someone just explain what those four arrows were? So what's the arrow from f of x to f of y?
F of the arrow between x.
Exactly. Yeah. Yeah. Yep. So yep. And what's the arrow from f of y to g of y?
The one from the natural transformation.
Yeah. So people would call that the component of the natural transformation. So the component of the natural transformation at y. Yeah. And then over here, from f of x to g of x, we've got that comparison map provided by the natural transformation. And then we've got the functor g applied to the morphism f. It says these two things commute. Okay, so now we better have two examples of natural transformations. A math example and a computer science example. You gave us the pi1 example, so what's the canonical natural transformation example that involves pi1?
I don't know, is it the F with the little star?
Probably not.
I think that's, you mean the functor, just on morphisms.
Yeah,
Yeah.
yeah, or yeah.
You pick different points, like go back to the ring. I don't know.
Yeah, you actually
Something like that.
can do that. So how would you do that?
I'm not sure because like we're in the pointed topological space category. So
Yeah.
it's
Oh,
chosen.
yeah. Okay, maybe. Okay, so maybe that. Yeah, you can cook something up there, but I agree. Okay, it's maybe a little complicated to say. Well, maybe let's do a kind of groupy example. If I gave you an abelian group, and I wanted to define a functor from abelian groups from groups to abelian groups.
Quotient by the
Yeah, actually, this is going to be a bad example, isn't it? It's not an actual transformation. Okay. Yeah. Okay. Sorry. What's a good example, Kelly?
Determinant?
Oh, tell us the determinant example.
Well, I'm trying to remember.
Okay.
But you take GLN and GL1. There's always a natural transformation.
Oh, fancy. Okay. So what were the? Okay. Kelly just said GLN. What did he even mean by GLN there? He said GLN was a function. He was defining a natural transformation between GLN and GL1. So how the hell is GLN even a functor? What's it taking as input? What do you feed GLN?
Vector spaces.
Not quite a vector space, no.
Perspective.
Field. And then
Yeah, a field will do. We can probably be a bit more general even. We could probably even just say a ring. Yeah, so you can look at.
The module.
What's that?
It gives you the module or the matrices.
gives you invertible
It gives you the invertible matrices with entries in that ring. Yeah. So GLN takes a ring and it spits out. In fact, it spits out a group. So it's a functor from rings to groups. And in fact, this is one where there's always this argument, like when you write GLNR, like what order the N and the R should come in, and whether the N should be a subscript or so on. But there's maybe a good argument that it should be GL subscript N, because then it's obviously a functor ready to eat R and spit out GLNR. And in fact, this is the whole point of algebraic geometry. Okay, but then there was a determinant. What the hell? Okay, how is the determinant an actual transformation? We've got these two functors from rings to groups.
If it's an invertible matrix, then its determinant is invertible in R.
Yeah, well, in particular, we could say in GL1R. Yeah, so GL1 is sort of just is the same thing as the functor that picks out the units of a ring. That's another functor from rings to groups, pick out the units, but it's the same thing as GL1. Yeah. So determinant takes an n by n invertible matrix and spits out a unit, something in GL1. Okay, and it's exactly a comparison map in this sense. It's just a morphism in groups. I mean, determinant is a group homomorphism. Okay, so it's something that compares the result of GLN acting on a ring with the result of GL1 acting on a ring. Awesome example. Okay, so det as a natural transformation from GLN to GL1
Didn't work right.
as functors ring to group. Okay, but we better probably have a computer science example as well. We've only met two functors so far, list and option. So we better have an example that uses those. Can we build an actual transformation in either direction? In fact, there are lots and lots of natural transformations between these guys. So what do we need to do? So all that we need to do is, for each type alpha, we need to give a function from list alpha to option alpha. That's an actual transformation. But it needs to, okay, so, well, so who can give a function from list alpha to option alpha?
Take the first entry and say sum that. Or
And it's empty, then it's not.
Yeah, and make sure you say none if the list was empty. Yeah, okay. And there are tons of things we could have done. We could have said take the third entry if there is a third entry, and otherwise say none. So there are lots of variations you could do, or take the last entry even. Okay, so is that really an actual transformation? We need to check this naturality square. Okay? So this is called a naturality square because usually you draw two morphisms that way and two morphisms this way. Okay? My ASCII art isn't good enough. Okay, so does head as a natural transformation from list to option satisfy the naturality square? So what's this saying? So this is saying we've got a function from list alpha to list beta, and that function is just going to be defined by take your original function from alpha to beta and apply it element-wise, apply it to every element of the list, and then we're going to take our list alphas Oh, sorry, well, let me not change letters. We've got a list of x's and we turn it into a list of y's, and then we turn it into an option of y's by taking the head. Okay, or we could take our list of x's and turn it into an option of x's just by taking the head, and then we could call map, which just applies the function to the sum if it was a sum, and otherwise left it as none. And obviously those two things give the same answer. Okay, so what's something of a non-natural transformation here? So I just need a function from list alpha to option alpha, but I want it to be stupid, so it doesn't satisfy this law.
Sum the squares of the elements?
Yeah, okay, so the problem is that didn't quite work, because remember, list here was just a functor from type to type. So the problem is there's no promise that the types have any additional structure. So you can't necessarily square them. Yeah.
You like send. You take it and send it to some like constant value.
Yeah, yeah, so you've got to worry.
Yeah, exactly.
Yeah.
None of those words. Just sending everything to none.
Yeah, so the function from list alpha to option alpha that sends everything to none is perfectly natural. Yeah. It's boring, but it's still natural. Yeah, so I think maybe without...
Oh, you could say like
What
if
do you
the
do?
list has, still take a head, but if the list has 3 elements, just randomly send it to none.
Ah. So if the list has
But the
3...
fact that there's 3 elements wouldn't change if you apply a function to each entry, right?
Yeah, isn't that natural?
It'd be something like if the list is of this type, do something really, really stupid.
Yeah, I think it's...
If the list has repeated elements or something.
Even then, you're kind of assuming some extra structure. Like, in some sense, that was as bad as Aaron's example. He needed a ring, but you need decidable equality.
But as long as function application over equality, is sensible, we'll still have the problem I had anyway.
Huh.
If you could do something like pick the minimum element.
Yeah, but
That would be-
again...
That's
You
even
can take
stronger
it-
than mine.
Hang on.
Yeah.
Why did my thing work?
Oh, okay, so Keely's example is
Sorry.
pick the third element. No, sorry.
Pick the first
Pick
element
the first element.
and do the normal thing you would do, except if the list has 3 elements.
Yeah. Always say none.
Yeah.
But then the function from the list to itself doesn't change the length.
If it has
Yeah.
But then, so one way you take the head, and then you just apply the function. So you should get, if you start with a thing.
Oh,
Yeah, it does work.
yeah. Okay, good. Okay, yeah. Okay, does everyone see what happens? So if we, no. Oh, I'm so confused. I don't see.
Do you want to draw the
Yeah,
square?
draw the naturality square. Chase the diagram. Let's have a diagram
It
chase.
does work.
Let's have a diagram chase. Excellent. Okay.
Is head a map
Well-
from alpha to list alpha?
Yeah,
Oh, you've drawn the arrows backwards. Yeah, then maybe they should have been list alphas and option alphas.
Yeah, what am I doing? Yeah, sorry, yeah. So, alpha. Okay.
Okay. So now we plug in 1, 2, 3. So you shouldn't write head here. You should write like head prime because it's like the evil head.
Sure.
Okay. So what happens? Yeah, this is not.
It's gonna be
It's
fine.
natural. Yeah, it's just natural. Yeah. Like where does it go? On the right, it gets into none because it had 3 elements. Yeah.
The bottom it still has 3 elements.
It still has 3
Makes
elements.
sense for none.
Yeah, unless your map somehow changes the length of the list.
No, but it can't
But
because
it
you're
can't
running
Yeah,
a
be
because
list.
it has to be of the single things, yeah.
Yeah. Yeah, so this is a confusing feature of the computer scientists not knowing about categories other than type. It's really hard to write down non-natural things for functions from type to type. We probably should keep going rather than spending a whole day talking about category theory. But everyone should think about an example of a non-natural transformation. Not necessarily from type to type, somewhere. Make sure that you can convince yourself that the naturality square is not trivial. Okay.
Maybe one last point just on this is that
Yep.
natural transformation the other way
Yeah.
can actually be useful like programming. And
Okay.
maybe,
So what? Yep. Give us the example the other way.
like, maybe, you know, in lean is called option.toList. Which does the, what could you do? You can do a singleton list if you have some alpha, and otherwise you can choose an empty list. And you could use this to maybe implement like this filter map function where you want to map over a list of alphas with a function that isn't just from alpha to beta, but is from alpha to, I don't know if anyone can see now, option beta. And that'll give you a list of betas. And this is a real function in lean.
Yeah. The idea is that because this function goes from alpha to option beta, it's just got the option of dropping things from the list as it goes along, transforming only the ones it wants. Okay. Yeah. In fact, that map will be a morphism of monads if we let's not go there. Okay. So the reason I wanted to talk about natural transformations is I wanted to just say a little bit about what a monad involves. So a monad is a functor from type to type along with, so let's call it M, monad, along with natural transformations. And what are the usual letters for these? No, T is the usual M.
Oh,
This is eta and mu. Yeah. Okay. So let's call it. Okay. Let's call it the monad T. Okay. So eta from 1. So 1 is the functor from type to type that does nothing. Okay. To T and mu. This is slightly confusing from TT to T. So what does TT mean? It's just the functor applied twice. Okay. So if it was the list functor, it's just the thing that takes a type and returns lists of alphas. Okay. And these two natural transformations are exactly now this extra data of pure and bind that we were sticking into our monad. Okay. So what does that mean? So i.e. For each type alpha, the component of mu at alpha is a function from, well, the identity functor applied to alpha, that's just alpha, okay, to T alpha, okay? And that was exactly the function bind that we had to define in our monad. And the other thing is for each type alpha, the component of mu, sorry, I wrote mu, but I meant eta there, sorry. Eta is a function from alpha to T alpha. And the component of mu at alpha is a function from T of alpha to T of alpha. Okay? And hopefully, I'm such an idiot, sorry. I'm getting everything backwards. This one was pure. Pure was the one that was the function from alpha to T alpha. And hopefully this one is bind. So let's go back and see what we were meant to be doing for bind. Maybe we can just do it down here. Oh. Ah, my comments are docstring comments. Lena's complaining. Oh no, that's not what bind is. Oh, what am I doing? Yeah, bind is not that component. Yeah, I mean, what that actually is join. Join is the thing that takes a list of alphas and returns a list of alphas. Why didn't we have to provide join here? I suspect it's because someone else is filling in join for us. No?
So
Where's-
it seems like it's not
yeah.
explicitly there. If you go list.bind is join of map. I'm confused, but I'm trying to help it.
Huh. Okay. Well, yeah, I don't understand my monads. Yeah, okay. How exactly you get monads on the computer science and math sides to match up? We're missing something there. Okay. There is some way of doing it. They actually really are the same thing, but I didn't think about it beforehand, so I've got it wrong. Possibly in a moment, Keely will reveal to us what's going on. Okay, so the monad that we need to care about. Well, okay, so a few things. We want to understand what this guard was doing in this do block here, which threw out some values. We'd like to understand the state monad. So let's actually maybe do that let's maybe build the state monad ourselves. So let's just define state to be, so state depending on sigma, to be the function from, sorry, what do I want to do? Yeah, and I need another type here, alpha type. Colon equals. Oh, state's already defined. Oh, that's annoying. State underscore. Okay. So, what did this do? So here it's a little bit confusing. Here I want to think of sigma as being fixed. Like here we've got sort of states with internal data sigma, and then after this this part here is the monad. It takes a type alpha, and it sends that to the type of functions from sigma to sigma cross alpha. Okay. Now let's build a monad instance on that. Oh, sorry, we need to, of course, sorry, I said that sigma was fixed, so we've got to fix a sigma. For each type sigma, we're going to have a monad.
What does the underscore on state do?
Nothing. It was just because the word state was already taken, and I wanted a different identifier. The problem is that state is already probably defined to be exactly, yeah, state is in fact defined to be basically this exact same thing as we're defining at the moment, because it's such an important idea. Okay. Okay, so we need to define pure and we need to define bind, and we'll see what Maureen wants us to define after that. Okay, so pure, what am I meant to do? So given an alpha, I'm meant to return a state sigma alpha. Okay. So let's fix the type alpha, and then let's maybe take a variable a, and now we're meant to be returning a state sigma alpha, which remember is a function from sigma to sigma cross alpha. Okay, so let's take an s, which I'm thinking of as my state, and now I'm meant to be returning a sigma cross alpha. Can you see how we could do that, given the data we've got so far? Yeah, SA, I think. But yeah, there's only one possible way we can respond at this point. So let's say SA. Okay. Okay, and what is bind meant to be doing? Bind is this complicated mess. Okay, so let's just write some lambdas to pull out the arguments. So here we've got a state, something that produces a new state, and we're meant to produce a new state gadget. Okay, so but remember these states are secretly their functions. Okay, so let's pull out an f as our first argument, and then maybe let's call that one k. And now we're meant to be producing this function. So let's take an s. Okay. What can we possibly do at this point?
Is it possible to pull the alpha out of that?
Can you pull the alpha out of it? Well, so remember what f is. F is a function from sigma to sigma cross alpha. So you can get an alpha, but the only way to get an alpha is if you give it an s. Okay? That's just the only way to proceed. Yeah? Can we do that? Yeah, we've got a sigma available. S is a sigma. So we could stick that into f. Let's just write that. So let's say have p f s. Just to note, we could do that if we wanted to. Okay? And maybe let's, at this point, clear s, since we've used it up. And maybe let's clear f as well. Okay. So what do we still have going for us? We've got k and p, and our job is to produce a sigma and a beta.
kp.2 would give us
K of p.2, yeah, we could feed that, yep, we can feed the second component of p into k, yep, so let's maybe have q equals k of p.2. And at that point we've probably used up k, and we should think of ourselves as having used up the second piece of p. So we're almost there.
And then using p.1.
You don't know p.1, no, because p.1 is a sigma. Well, so p.1 is a sigma. We need to produce a sigma cross beta.
p.1 cross q.
But q, remember, is a function that takes a state and gives us a state and a beta.
We didn't need sigma and q.
Yeah, we can feed p.1 into q. And what will we get when we feed p.1 into q? We'll get exactly a sigma cross beta out. Okay. So we can now say exact q p.1. And that did something. Now, we wrote that with no understanding of what we were doing. We just had a bunch of arguments and functions, and we were just like feeding things in. Maybe we were using the principle to like only use things once. Like once we'd used up an argument, we didn't use it again. But we wrote that program having no idea what was going on. Okay, so let's interpret what we should be wanting to do here now, and then I want you guys later to go back and read this program and see that it really implements this. Okay, so the way that you should think of one of these state underscores is it's just a function that produces an alpha, but it's a function that depends on secret mutable state. Okay, we're used to, yeah, so.
Why didn't we just use
Yep.
the s that we threw away as the sigma instead of p.1 at the end?
Yeah, good question. So we did have a choice there. At the end there, we had two sigmas available, and we could have spat out either one. Yep. Okay. One reason is that if I use this idea that I only want to use each piece of data once and then not use it again, that kind of invalidates. We had to use the first sigma. Remember that first sigma there was our p.1. Okay, and so we had to get a beta. We had no choice but to feed that into Q. So in some sense, if you believe you shouldn't use things twice, then that uniquely defines this program. But otherwise, yeah, there are definitely choices.
But you just discovered how to implement lock tactic state.
Shh. Yeah, we're doing the first question here at the moment. It turns out, but it's not obvious. Yeah. Keely just told you. Keely just explained that Isabel knew how to answer question 1. You'll hopefully work this out. I agree, it's confusing now. Okay, but this will become clear once we interpret what these sort of sigmas are. Okay, so this state underscore sigma alpha, you should think of it as just a machine that produces alphas. It's some function that goes away and calculates an alpha. Okay, but it relies on there being a mutable state in the universe. So there's some sigma. So sigma represents some sort of internal values that we keep as the calculation goes along. So this function here is allowed to go and look at the current internal stored value. Using that, it's allowed to compute an alpha to return as a value, but then it's allowed to stash away again a new state, so that the next function that gets called is allowed to look at that stored state, do something, return a value, and stash something away again. And this is exactly what was going on in pure and bind. That takes the internal state, the sigma that's currently available, completely ignores it, returns a constant value of A, and stashes away the same state that it was given. Okay, what the hell was bind? So in bind here, what we had was we had an S, which is sort of an initial state. Okay, and then we had two things. We had F, one of these functions that produces an alpha, possibly mutating the state as it goes, and we have a K, which given a value of alpha, is a function that produces a beta, again possibly mutating the state as it goes along. And if you read the bind that we've written, it really represents exactly that interpretation of state underscore. We took our state, we ran the function f, producing its value, and stashing away whatever new internal state it provided. But we're doing the stashing away here in the implementation of bind. Then what we did is we took that alpha that we produced and we stuck it into K. Now we've got some function that produces a beta, but it needs to know which secret internal state to operate on. So we give it the secret internal state that F had produced. So F had updated the initial state S, produced a new state, and we feed that into the result of K. And then, of course, according to the semantics, we're meant to be finally stashing away the state that K produced, so that whoever's working next can operate on that state. And that's why we shouldn't go back and stash away the intermediate state, because then whatever update K wanted to make to the secret internal state wouldn't have been reflected in whatever happened next in the computation. Awesome. Get your head around that, and you know what's going on in monadic programming. It's fine if it's still confusing. Okay, so this thing we just defined here is universally known as the state monad. And you can go look it up and read about it, and find confusing Haskell tutorials about it, and things like that. Okay.
I have a resolution to the thing.
Okay, let's have an interlude about lists.
It's not
About monads, yeah.
Yeah, it's not too much of a big deal. So we just wanted to know what, we had bind, which I'll write big. Bind was from list, took a list alpha, and an alpha beta. And it was meant to give us a list beta. And the problem was this doesn't look like what mu was, or join. Join, which is just meant to take a list alpha, list alpha, into a list alpha.
No.
But the point is that this is actually, if you have an ambient map lying around, like so, you know, somehow the fact that list is a functor isn't bundled into the actual like function list in Lean, you know, then this is the same data, because you can recover this join, the mu, from bind by just putting in the identity map list alpha to list alpha in here. And what will this do? Bind then says it will give you a way to take a list of list alphas and produce list alphas. So exactly putting in the identity map list alpha to list alpha in the slot recovers that. And if you look at the implementation of bind, bind just maps, actually just maps functions over the list it's given and then joins them. So this is really, they're both equivalent if you have an ambient map.
Great. Okay. Yeah. So very good. Okay. So this was the state monad, and when we're writing tactics, this is exactly what's going on. So let's. Oh, I guess we should actually use the state monad here a little bit. Let's write a little program in this state monad. So let's write. So we better. Let's see. So we've built our state monad. So what program do I want to write? So
The state could be the number of things that have been bound.
yeah. Okay. What if we just have our internal state just to be a counter that just clocks how many steps of our program we've run? Okay. So how are we going to? Well, no, sorry. Well, that's not quite the example I want. What's the?
It can be like a string of output you can optionally append to.
Sure. Okay. Yeah. So how do we write this?
You probably need like one more function that's like output that you pass a string and adds that to the global state.
Yeah. I feel like I wrote a nice example of this just not that long ago, and I'm blanking on where I put it. Oh. There was some tactic I wrote recently. The monadic lazy list testing file uses the state monad to avoid writing trace statements. Okay. Let me see if I can show you this. Maybe this example is too complicated, but maybe it's not. So, test monadic lazy list. Okay, so this is some crazy weird thing about lazy lists, some programming thing. Oh no, this is going to be too complicated. I mean, you can see here I'm using the. Yeah, this is exactly the example you just said, where it's like appending something to a list, to an internally stored list, and doing stuff. But yeah, I'm not sure I really want to explain it. What does reducible do at all?
Yeah.
Yeah. So you'll probably remember finding yourself writing dsymp open square bracket something anything that's reducible just falls apart immediately in the face of desimp, even if it's not named in the square brackets. It affects a few other things. There are a couple of places where when lean is rewriting or trying to match something, it will automatically unfold anything marked reducible in that step of trying to make things match, depending on internal settings. I'm actually not sure if the reducible matters there. Oh, apparently does. Oh, yeah, it's probably to automatically acquire monad instances for S, so that when type inference is trying to look for a monad instance, it automatically unfolds S and then sees state T and picks up monad instances for that. Yeah, okay. Yeah, I'm not sure I actually want to do this example now. I feel like it's probably too complicated. Okay. Okay, let's just go on to the tactic state stuff, but a good exercise I think is to try and actually use this state monad we defined here yourself. Actually write a do block where the do block is doing something using this. Maybe I can write an example and show everyone. Okay, so let's work out what's going on when we actually write a tactic. So let's. Sorry. No. Before that, a few more things I want to show you. Let's go back to some of these do blocks that we wrote, and let's actually see what they're actually doing. Okay, so I'm now going to print Z and see what was inside of that Z that was written with a do block. So notice that the do block is purely syntactic sugar in the parser. Like the definition has no do's in it. Instead, it has these crazy greater than, equal to symbols in it. Great, very helpful. The first thing to know about this stuff is Mario's monadic cheat sheet. Hopefully Google is smart enough. There's a tactic writing tutorial, which might be very helpful to read again, and again. And way down at the bottom, there is a very helpful guide to what the hell the little strange squiggles that appear when you're programming with monads are. And so this greater than or equal to is the very fundamental one. Which, well, is exactly what's produced by doing this. When we pull something out using that bind arrow in a do block, where this is just the syntax that represents that. So it's basically saying, well, so MA should be some monadic value, either maybe a list of alphas or a tactic alphas or something like that. And then F is something that takes the sort of the sort of wrapped up type, the thing inside the monadic thing, and produces a new monadic thing of the same type. Okay, and okay, fine. Okay, so sorry, I was going to stick that URL here so we can find it. Okay, so the way that you should read this is sort of take each thing out of X and then shove it into this thing. So this is some function that takes a natural number and produces a new list. Remember, g of x produced a list. And then this says take everything out of the result you get from that and shove it into this, which is just a function that returns individual values. If we turn off notations, all of those greater than, equal to symbols will disappear, and we'll see it's all been compiled down to something purely in terms of bind. Okay? And so you can see that what lean did when it had a do block was it just went away and looked for a monad instance, and then just interpreted these arrows as these bind statements. Yeah.
Is that capital X the input?
Yeah, that capital X was the first thing we put in there. Z was not a function that took any arguments. It just It just started. It just took every element out of big X, and then took every element out of G of each of those elements, and then returned them. And so, okay. Okay. So let's try and work out now what tactic is. Okay. So tactic is defined as interaction monad, tactic state. Okay, maybe that's a little bit confusing. There are two things going on here. So the interaction monad part maybe is worth not worrying about too much. It's basically something that takes one monad and turns it into another monad that has sort of some error reporting features. Let's for now just jump down further into tactic state. And we're very sad because tactic state, oh, sorry, okay, no, I screwed up, sorry. I lied about what interaction monad is. We'll go back and look at that in a minute. Okay. Tactic state is just a meta constant, meaning it's not even defined in Lean. We've finally drilled down to the bedrock and are about to fall through into the C++ underworld of Lean. There's not a Lean implementation. We've finally hit C++. So a tactic state is just an object that represents all of the current data in the middle of one of our proofs. So it holds in particular the current list of hypotheses, the current list of goals, also a whole lot of information about the current meta variables and how they've been unified with other things. The fact that question 1 on the assignment, or question 3 or 1 or 3, I forget, one of the questions on the assignment gives you a hint about a tactic called lock tactic state. You might imagine that it's interacting quite closely with this one. Okay. So you should think that tactic state is just a data type. It's just like, think of it as just something like a list of integers and a list of strings and a list of somethings, just that represents what you see in that right-hand window when you're in the middle of a proof. Okay? Okay. So there's nothing exciting in that. It's just a C++ representation of a whole lot of crap. Okay, so let's go back and instead look at interaction monad, which is the interesting bit. Okay. So what does a interaction monad do? Well, given some type called state, and this is going to be this exactly like the sigma in the thing that we just did, okay? That is like that's the stored secret state that gets passed along from step to step. And given an alpha, another type, it's just a function from state to result state alpha. Now notice that in our example that we did a moment ago, we actually wrote something very, very close to this. We just wrote state cross alpha, okay? And they've just decorated this with, they've just got result state alpha. So let's just look up result and see what result is. Result is exactly here. It's just an inductive type that has two constructors, one called success that consists of a pair, an alpha and a state, and another inductive type, another constructor called exception, which contains a bunch of information about how to format an error message to show to the user. Okay? So basically, it's exactly the same as the one that we just constructed. You feed in a state, and it produces an alpha and a new state, except that it's also got the possibility of failing in a way that reports some error information. So there's that slight addition to what was going on. Okay, and presumably we can also go back here and summon an instance of monad tactic invalid definition. It uses the untrusted declaration tactic, even though I just want to know what its monad is. I need to say meta. But that didn't help me because I wanted to print it. So print def tactic monad, print tactic monad, and then we'll have found where it was. And indeed, what it actually found there was this bit here, interaction monad.monad. Okay, so let's print interaction monad.monad and look that up. Okay, it's got a map and a pure and a bind here, and I suspect that if we went and looked them up, they're basically going to be the pure and the bind, or the pure and the pure and the bind that we just wrote a moment ago. If you go read these, it'll be slightly dressed up versions of those that also do this handling of error reporting, okay, and handling the fact that a tactic is allowed to fail. Okay, so remember in our version of bind that happened back here, this was basically saying we've got two steps of our program. This first step F, and this second step K that depended on the output from F. And what bind was doing was just sort of gluing two steps of a program together into a single step of a program. And so, of course, if you have the possibility that F could fail, you've got to decide now what to do. If F, instead of returning a pair, could have just said, I give up, what's going to happen? Well, it's actually going to say, I give up, and still give you a state. So all that's going to happen is you're going to, in the event that F fails, you're just not going to even attempt to run K. You don't even have an alpha to run it on, so you can't. You'll just return whatever state F did, and as well go out and print the error message that the failure state in F produced. Okay, so okay, fine. Okay, so the monad instance underneath tactic really was just a special case of the state monad that we just wrote, with a little bit of extra information about handling errors. Okay. So let's write a really easy tactic now. Let's define swap, a tactic that this is probably already built in. I'm sure there's already an interactive tactic swap, but let's do it anyway. Okay, so we're going to write a do block, and it feels like what's going on is that we're writing a little imperative program now, but really what's happening is it's not an imperative program. Each little step is one of these little state transformers. It picks up the current tactic state, it does something, and it hands back a new tactic state to be plugged into the next step. Okay. So what are we going to do? We're just going to first of all say, let's get the goals. And then let's, there's an important, open tactic, thank you. Open tactic, otherwise it can't get goals. But the problem is as soon as we open tactic, oh no, swap is not going to be okay. So what does this tactic do? It's not the awesomest tactic. What's that?
Swaps the first two.
No, the one I wrote here, but what I actually implemented. We're getting towards that one.
That's the dream.
That's the dream. What does this one do?
Gets the goals and does nothing.
Yeah, so in this case, what you should think is that get goals is a tactic that probably doesn't update the underlying tactic state at all. So in terms of this thing that takes a sigma to a sigma cross alpha, the sigma is going to pass through unchanged, and the alpha will just be pulling out from the huge package of data that is a tactic state what the current list of goals were. But we then discard that. I mean, in this case, we take this GS and we don't do anything with it. So that side effect just gets discarded. And skip is just a tactic that does nothing. But remember, every step in one of these tactics, every tactic is a tactic alpha. Every step has got to return something. Okay? And in one of these long do blocks, the return value is just the return value of whoever came last. Okay? So sometimes what you might find is that the last tactic you really want to run is a tactic that produced some value, but you don't care about it. You want to return a tactic unit. So you just stick on skip at the very end. Because a final extra step that just takes the tactic state, passes it on unchanged, and returns the only value of unit, so that you're actually returning a tactic unit.
Well, yeah, I was just going to say, what's a unit?
What's a unit? Oh, yeah. Does everyone know what unit is? When we write tactic unit? Unit is just the unique the type with exactly one generator. Well, it's an abbreviation for P unit, fine, okay. And P unit is just an inductive with a single generator star, okay. It's the one element inductive type. Okay, so this tactic was not very exciting. What do we want to do next?
Swap the goal.
How do we swap the goals?
um,
So at this point, notice if we hover the mouse over GS, it says it's a list of expressions. Those are expressions representing the goals.
Like check the length or something.
Check the length. Yeah.
You have at least 2 goals.
Yeah. The really sneaky way to do this is that whenever you have one of these bind operators, you're allowed to use the pattern matcher on the left-hand side. So what we can actually do is we can deconstruct the result from get goals into pieces right away. So here we can write A : B : T. And then it'll take that list that get goals produced and deconstruct it into a first element, a second element, and then the tail, which will be a further list of expressions. So you have T is a, hopefully T is a, oh, you can't hover quite yet. Oh well. Oh yeah, P, no. Okay. You can't hover inside the pattern, apparently. Okay. But yeah, you can deconstruct it right away like that. So what are we going to do next?
set goal.
Set goals. Okay, so what's the call exactly going to be? We're going to go set goals,
V : A.
B : A. Let's say : T. Probably shouldn't throw away whatever those other goals were. And it's unhappy because, yeah, I needed to parenthesize that argument. Okay, so what is set goals? Set goals is a tactic unit. So it picks up, brings in the incoming state. It just rewrites willy-nilly what the goals are, and the alpha is a unit. It just produces no value. It's got nothing to report. Okay, so in fact at this point we could just remove the skip. Okay, because set goals is returning unit. So
What happens if you don't have 2 goals?
yeah, okay, so let's try it out. Example, true, : equals, begin, end.
True and false and true, and you can split.
Let's call ours swap prime, just so we don't get confused with the swap that already exists. Okay, so what does it say? It very unhelpfully says match failed. So match failed is basically saying I took the answer to get goals and I tried to unify it with this pattern, and I couldn't do so because it wasn't a list that was long enough. That's an extremely unhelpful message for a tactic to produce, and if a user-facing tactic does that to you, you should be unhappy. So how do you fix that? Well, of course, there's all this error handling business built into the tactic monad, as well as just this state monad. So some syntax to learn is you can always write a pipe at the end of a pattern of a bind, and then after that you can write fail. There must be at least 2 goals, and that then says try running this, but if the bind doesn't work, go do this. And now swap prime very hopefully says there must be at least 2 goals. Pretty good. So let's okay. It's very important to test your tactics as you write them. So we should document the fact that that was the expected behavior of swap by wrapping that in successive fail. You might think a bit about how successive fail is implemented in terms of the tactic monad. What does it do? It's kind of nifty and is related to whatever that third question is. So it takes the incoming tactic state, it runs the tactic in the parentheses, in the curly braces on that tactic state. That, remember, could either return a new state and an answer, or a failure notice. Okay, so it checks that it did return a failure notice, throws away the failure notice, and hands back whatever the state had been before we ran that tactic. So this is sort of an example where we're breaking the rule that we used to write the state monad. Remember this rule of like only use everything once? This one broke it. It fed the incoming state into the tactic swap prime, the thing in parentheses. But then when it failed, it sort of went back in time and took that same state that it had at the beginning of the day and just passed that back out again. Okay? Even though something had gone on inside running swap prime. Okay. So we'll document this, and we'll document it properly by actually completing the proof. So we'll write trivial, and then let's just have true and true split swap prime. Not very helpful because
True and 1 equals 1.
true and 1 equals 1. Excellent. Okay. Great. So this one we now should be able to prove by ruffle and trivial. But if we turn the swap around, it really won't work. You can't prove true by ruffle. So you can really verify that the swap was taking place in that. Awesome. Swap tactic. Okay. What if I'd misimplemented my swap tactic? What if I just said, if I was too much of a hurry to get on with things, and I just said set goals b comma a? Okay? Nothing goes wrong. All compiles. You're allowed to do that. You're freely allowed to call set goals on any list you like, whether they're a subset, a superset of the actual real goals. Let's see what happens. Example, true and 1 equals 2. Begin end. Split. How do I do? Okay. Split.
Use the real swap.
I'm about to use the real swap. This is so lame.
You can parenthesize the ands in the example, right? Would that work?
Haha. Maybe people haven't seen this notation. So remember what semicolon normally does. X semicolon y runs y on every goal that X produced. But you can also, after a semicolon, put a list. And then this runs those tactics on the respective goals produced by the first guy. So this runs skip on the first thing produced by split and runs split on the second thing produced by split. And that had the effect of splitting again on the second goal. Okay, so now we run swap, double prime. Sweet! We can do it, we can do it. We've got our theorem proved. Goals accomplished. We did it. And then there's a sad error message. Tactic failed. Result contains metavariables. So the things in the list of goals accessed by set goals and get goals are pure fiction. It's just bookkeeping, and you're allowed to modify them however you like. There's a lower level that's keeping track of what the real goals are at any given time. Okay, so what do we do in this state? Well, okay, if someone's written a tactic that if this ever happens to you, you work out which tactic that you used had a bug in it, and you're going to report it to the author of that tactic that they've got a bug in it. Because you should, without big red flags, you shouldn't throw away people's goals. But there is a tactic recover, or not. What? It's called recover, isn't it?
That's a real thing. Did you try that? Did you try without tactic dot? It works for me.
It works for you.
Yeah.
Unknown identifier recover.
It's try tactic dot interactive dot recover. That's what it's called.
That's misspelled.
Oh, I bet I don't have mathlib. Yeah, I'm just in a completely bare file here. Recover is in mathlib.
Well, I can tell you what to do.
Yeah, so I guess we need to import tactic.interactive at the top to get the basic stuff that everyone assumes is always there. I seem to have not compiled anything in a while. Oh, well. Here we go. Okay. Oh, I misspelled tactic. Okay. Okay, but recover. Okay, recover brings us back to the real goal that was there. Okay, let's work out what the hell recover was doing. Okay? Because that will basically explain to us how the goals are really kept track of under the hood. So let's jump to the definition of recover. Oh. Okay, this does something pretty simple and straightforward. It calls some tactic meta variables and then shoves the result of meta variables into the tactic.setGoals. So this is exactly the same as if we'd done do m left arrow meta variables comma set goals m. Okay, we're just passing the result of one tactic into another. Okay, so we better go look at meta variables because that's clearly where all the work is. And it's actually pretty simple. So there's a tactic result which returns an expression. So it's a tactic expra. And let's read the help text. It returns the partial proof, the partial term/proof constructed so far. Note that the resulting expression may contain variables that are not declarate in the current main goal. So let's actually go through here and see what's going on. So you can in fact always write little do blocks just inside a begin end block. So what I'm going to do here is I'm going to take do result and shove it into trace. Okay, and that prints a little trace message at that point, saying here's what I think the current result is. I think the current result is $M1. Okay, we've just got to. What's happened is that when you begin the begin end block, Lean creates a fresh meta variable. And the begin end block's job is to unify that meta variable with a concrete particular expression. Okay. So let's just put this do result business all the way through, and we'll see what happens at each step. So here it says just M1. Here it says something much more exciting. So what's happened? Well, we ran split twice, okay? Which basically said we want to build our result as the anonymous constructors applied to something. So now we've got 3 meta variables for the 3 slots that we're meant to put in there. Let's run swap. Oops, I cheated. I didn't even look at the result. But the result at that point is exactly the same. Okay? Because of course swap didn't do anything to the real result. It just did bookkeeping with the supposed list of goals that getGoals and setGoals has access to. And then we run trivial, and we look at the result here. And let's just work out why it changed in that particular way. So why did it change in that particular way?
You've done swaps. First 2.
Yeah, so at this point, the result had 3 meta variables in it. And those 3 meta variables were in fact the goals. Actually, let's do double trace printing here. So the other thing is we could do get goals, and we could pass that into trace as well. Okay, and so this says your goal is a list with a single element in it. And notice it's exactly the same meta variable in the result. What the hell? What?
I think it's not printing their secret numbers. I think it's deciding how to number them based on what it's being told to print, and then it's being called to format 3 separate expressions. I think it's just counting from 1 every time. I guess. It surprised me.
Ah, that's a little sad.
They do have secret numbers, but they're total garbage.
I see. So all these underscore numbers here. Yeah. Okay. What if I... Can I just run these through the pretty printer? Does it change if I run them through the pretty printer? No. Trace was already doing that. Do you know how I turn that on? Is there just some set option?
No idea. No idea. Purify method.
Oh, purify. Okay, that's the one I had, but the point is it's by default set to true, and I had to set it to false. Okay. Awesome. Okay, that's much more helpful. Yeah. So. Oh, but no, but they aren't the same, and I wanted them to be the same.
Is there any consistency over the swap, right?
You mean before and after I swap them?
Yeah. Okay, I have no idea how this works. What? Okay.
Sorry, yeah.
They're the same.
Oh, they are?
First is-
It does actually swap them. Swap the numbers, they just...
Yeah, so the first number is is volatile, and it changed from step to step, but the second number really was preserved as we moved things around. Who knows what the first...
So metavar is secretly 2 names.
Yeah.
2.
Okay, so there are 2 numbers attached to
Yeah.
the meta variables, and one of them just changes randomly, and the other one seems to be carried along.
Why
Okay.
didn't you do the whole name, though?
But it-
another secret name. Anyway.
The name at the start on mine doesn't change.
Yeah, I don't have that changing on mine either.
Really?
Yeah.
Oh yeah, I didn't either. What? But a moment ago, I was copying and pasting. Oh, no. Every time you edit, it changes. So that when I'm trying to do copying and pasting here, when I paste it, it goes and destroys all those first numbers.
There we go.
Oof. Okay. Okay. So, okay. Yeah. Take those numbers with a grain of salt. One thing to notice, though... Oh. Yeah, okay. So basically it's impossible to put these in comments unless you copied them all into a separate file and copied them all back in one go. So I'm not gonna do that. It looks like everyone is reading along anyway. Okay, so the things that we wanted to observe before we got confused by meta variables was that here we had 3 goals, and the result had 3 meta variables, and indeed they were exactly the same ones in the same order. Then after we ran swap here, there were 2 goals, but still 3 meta variables in the result. When we called trivial, we got down to 1 apparent goal and 2 meta variables in the result because one of them has just been filled in with trivial. Then apparently no goals, and then that missing meta variable is still in the result. And all that recover is doing is it's actually taking that result expression and it's doing a depth-first traversal of the whole expression object and just looking for anything that is a meta variable and collecting them as it goes through. And then just taking all the meta variables it found and resetting those as goals at the end of the day. Okay. Pretty good. let's. I guess there's one more thing. Oh, okay. Yeah, the final thing I want to try and explain today is a bit about what is contained in a tactic state. So what have we got so far? What? I mean, we're not going to definitively answer this without opening the C++ code, but what do we know about that's stored in a tactic state?
The set of goals.
Yeah, some list of goals, which may or may not reflect the. Yep, it's also got a result. The thing we're pulling out at each point along here. What's that?
Your hypothesis.
Yeah. So how do we access the local hypotheses? Yeah. So let's just write one. There's just a tactic called local context, and it gives you a list of expression objects. And so, for example, we could just trace them. And so now we could write a function that takes a natural number and a list of natural numbers and returns a natural number. And we can do this in tactic mode, and we can call show locals, and it tells us that our locals are n and x. Okay. Now, what would you do? So notice that it only gave you the names of them. Okay. What would you do if you wanted to find out the types of those things? That must also be stored in the tactic state as well, not just the names of the locals. So we've got something called infer type. So we can take each thing in the context. Now, you might be used to writing, if you've got a list of things, you can write list.map, and then just run a function that applies that function to each element of the list. So what we might try doing is do context.map infer type. And the problem is context.map infer type just returns a list of tactic expressions. It doesn't actually run the tactic on each element of the list. Okay? But this is what monads are good for, and there's a function mmap, which basically runs not that map, but runs that bind. It exactly runs, no. What does it do? What is mmap under the hood? Mmap is neither of those things under the hood. Okay. Yeah. Okay, but anyway, you can imagine what it does. You can see the type signature here. Given a function from alpha to a monad of betas and a list of alphas, it gives us a monad of list betas. Okay, and then we could trace that as well. And now when we do show locals, it's going to print two statements, nx and nat, list nat. Okay? So yeah, if you didn't understand the difference between map and mmap there, make sure you do at some point. Okay, yep, so it's got the things in the local hypotheses and their types. Something to be a little bit cautious of here. The local, if you've got multiple goals, there are, they can have different local hypotheses. Yeah? Like when you do induction or something, like only one case might have the induction hypothesis. So what's going on here? Yeah, I mean, local context is really just returning a list of expressions. So notice it says return the hypothesis in the main goal. So local context is actually interacting with this bookkeeping device, the list of goals according to set goals and get goals. Secretly down in the tactic state, each individual meta variable, whether it's in the list of goals or not, has its own local context. But the only way you get to see that local context is to push that meta variable into the top of the list of goals and call local context to read it out. Probably there's another way to do it, but I don't know. I mean, we could probably look in the implementation of local context, actually. No, local context is just a meta constant. We've fallen through the bedrock into the world of C++.
It's not actually a constant, right? Like secretly, it's been overridden.
Yeah. Okay. Okay. So there's each meta variable has a local context. All those bits of local context have types that we can access through infer type. We've got the bookkeeping device of the list of goals accessible through get goals and set goals. We've got a target. So we've got a result. Oh yeah. What's target? So this prints nat. So target returns the type of the main goal. So that means it runs get goals. It takes the first element out of that list. That's just going to be some meta variable, but it runs infer type on that meta variable, and it gives you that. Every meta variable has a type. I mean, that's sort of the point of meta variables. Okay. Let's write one more tactic. We probably should stop pretty soon, try 0 on all goals. Okay, so this tactic is going to do what it says on the box. It's just going to try and use the answer 0 on every single goal. So there's a bunch of ways we could do this. We could just write it in. We could sort of write it in backtick mode, that is in interactive mode, where you just do something like all goals try exact 0. Will that work? Yeah. Okay. That's one way to achieve it. Yeah. Looks good. Okay. But let's do it sort of the really under the hood way, where we. Okay. So what we're going to do is we're going to get the goals. And then each of those goals is a meta variable. And the fundamental thing that you can do with meta variables is unify them. So there's this very important tactic. Unify, which again is down in C++. And it takes two expressions, T and S, and some optional arguments that modify the behavior of how unify works. Let's not worry about those as a moment. And it checks if they can be unified. Now, unification is something with side effects. That is, the tactic state gets modified as you call unify, because if the T and S have meta variables in them, and it's possible to make the expressions look the same by assigning particular values to those meta variables, it does so, and it does so permanently. After the unification, those meta variables have those values attached. So what we're going to do is we're just going to, for each of the goals, we're just going to call unify with 0. Okay? So we're going to take the goals, and how are we going to do this? We're going to do mmap again, and then inside the mmap we're going to write a lambda. So for each goal G, let's just call unify that goal with 0. But I can't just write 0. Why can't I just write 0?
Because 0 has lots of meaning.
Yeah, but in particular, 0 is back in the real world. 0 is like for producing a natural number or something. We want the expression representing 0 at this point.
Exact 0.
Well, no. So I mean, exact is some tactic that actually calls unify. You'd be going in circles if you if you used exact at this point. No, we just need to literally build the expression 0 at this point. So why don't we just do that here? Does that work? Maybe I need some extra backticks. There we go. Okay. So yeah. Along with there was a moment ago I pointed you guys to Mario's monadic cheat sheet on that exact same file. A few lines further up, there's another cheat sheet. The backtick cheat sheet. Oops. Which is for working out how to make these backtick expressions. We can build expression objects by letting you write honestly in syntax inside them. But there are many variations, and it's confusing. But there's a cheat sheet. Okay, but this one, yeah, hopefully produced the expression representation of 0, and maybe to be really careful, we can even write 0:nat there to tell it which one we want. Okay, so now we can call unify with z, which will attempt to, for each goal, unify it with that expression that we just made. It gives us an error message at this point. What does that error message mean? What's the solution?
Skip.
Yeah, awesome. Yeah. Exactly. The problem was that our last thing, the gs.mmap, it collected all the return values of running unify on all of the bits, and returned us the list of all those return values. So it gave us a list of units, but we only wanted a unit. So yeah, so a great solution is to just put skip at the end. But this happens so frequently that there's just all of these mmap and mfilter and so on have another version where you just put a prime on them, which says, and chuck away the answers, I don't care. Okay, so did this work? Oh, we've already defined this tactic. Okay. We probably better try this out at this point. Def bar nat times int. We better give it something it can't do. Well, let's give it something it really can't do. List events. Okay. And let's do our same little splitting trick. Where was our split trick? Okay, we've now got 3 goals, a nat, and a list of integers. And so let's try our first one. Try 0 on all goals. Well, that worked pretty well. It got rid of the nats and it left us with a list of ints. Okay. Let's try our other one, and it says unify tactic failed to unify some meta variable, which should be a list of ints, with 0, which is a nat. And it failed, and it left all 3 goals. Why is that?
Because the tactic failed, so it reverted everything you did.
Yeah, so usually each step will usually if a step fails, it returns the tactic state to what it was at the beginning of the failure. I mean, you can actually make that not happen, but the point is that mmap here was running many tactics, and it only succeeds if every single one of them succeeds. And so basically what happened is just that we forgot to reproduce the try that we had in our original tactic. We just didn't do that in this version, okay? So we can just call, since we're in inside mode, we have to call it try core, which is the non-interactive version of try. And then that one works. Cool. Okay, but I want to show you one more thing. Okay, sorry. Okay. Okay, I'm about to run out of battery as well, so I'll only show really one more thing, but you can get going. So How do I do this? Oh, okay. What I'm going to do is I'm going to trace the goals here, and I'm going to trace the goals afterwards, and then I'm going to do nothing, just to see what happens. Okay. Oh. I wanted to demonstrate instantiate mvars. When do you have to do that? I thought you had to do that.
I think you still do, but the pretty print is just being smart.
The pretty print is doing it. Okay, let's not bother explaining instantiate mvars today. We've done enough today. Awesome.
It's because you're not comma off this line.
What was that? Oh, okay. Okay, I think that's probably more than enough for the day. Yeah, I'm happy to stick around and answer questions, but my battery's about to die.
If you turn off PP to instantiate in bars, then you won't do it.
Oh. I didn't even know that was an option. Okay. That's for another day. So Kevin Buzzard, who is a number theorist at Imperial, a fairly famous number theorist, he proved some big things back in the day, well, still today, I guess, has been obsessed about, he really wants to do sort of a big piece of modern mathematics in an interactive theorem prover. None of, like, the previous sort of big theorems that have been proved have all been decades old stuff, and somehow pieces of mathematics that are like are hard and have many cases and are complicated, but are not like don't require you to have taken 20 courses in the right order before you know all the bits of math to do it. And so he really wanted an example sort of unlike these, and so he's been wanting to define perfectoid spaces in Lean. So these are some pieces of algebraic geometry, modern number theory, that this guy, Peter Schulze, one of the last Field Medal winners, is famous for. I mean, he's an unusual case where he sort of has a Field Medal for a definition more than a Field Medal for a theorem. Like, the definition is so good. I mean, there are theorems too, yeah. So Kevin is at a conference in Austria this week that I wish I had been able to go to actually, on interactive theorem proving in mathematics, and he's giving his talk tomorrow morning Austria time, and he really wants to announce, like, I finished the definition of perfectoid spaces, it's here. And there's now I guess approximately 24 hours to go before his talk, and there is definitely not the definition of perfectoid spaces, but yeah. He's definitely not slept in a day or two, and I didn't get very much sleep last night. I think I might not sleep again a bit tonight. Sorry that your assignments aren't getting marked. Kevin really wants the definition of perfectoid spaces. It seems like, I don't know, it seems fun to try. But anyway. Mitchell is lurking there, wanting to talk about his honours project with me.
Not that I really
Oh.
enjoying watching the lead.
Okay. Excellent. Let me